So how's everyone doing? Are there any burning concerns?
I have a question on the homework. Except for the code and the answer, what would you like us to write, like explanation-wise?
So increasingly, I want you to decide that. I want you to write a report of your findings that explains how you do it. I mean, give us your answer and motivate it the way you would write it in a scientific paper. You would say, here's the problem. Here's how I go about it. In other words, the assignment is not a number at the end. We want to see your thought process. That means that not everyone, or rather, everyone will do something differently. Everyone will do something their own way. And I want you to explain to us how you go about it your way. Does that make sense? It's open-ended deliberately. So have you thought about it? Do you have any specific questions?
So I think I understand like the concept of like you make a guess for the location and time, and then you need to use this Geiger's method to iterate over and over until you minimize your error and get a good answer. I guess my question's kind of broad. I guess I don't really know like how to start like writing the code. Like I have the equations, I did the readings, but I guess I'm confused. Like what is D? What is G? What is M? Exactly.
Let me sketch that a little bit in that case. So where we ended was here, right? I think what you should do minimally is the following: how to codify this, right?
Yeah, I guess that's my question.
I think you should do the following. You should write, you always begin by writing a function, right? So this function will be called solve this problem, all right? This function is going to have sub-functions. If you say, I don't know what G and M is and so on, I say, well, start thinking about it like this. One function that you definitely will need, which is a sub-function, is going to be something that predicts the time in the forward model. What will the forward model have? What goes in, knowing that what comes out is a time.
Would it be a distance?
Yeah. So let me pick the symbol so it's easy. I'll say not just necessarily the distance, but you might as well say the station location matrix, an event location matrix, which I'll call M. What else? You said distance. So distance is in the difference between S minus M, right? So where are the stations? You will need that, right? That's an X and a Y and a Z. Where is the event, the earthquake? That's an X, Y, Z, and T. What else do you need?
Velocity.
Yep, the speed, which is fixed here, but how about you leave this as an input so you can change it? Because maybe I'm wrong about the velocity, the medium speed. Okay, you will write a little function that computes the time it takes for an XYZ time to connect to an XYZ in a medium of speed V. Okay, that's G. It's not a matrix, it's an operator, it's a function, it's a curly G. All right, then you'll need something which I'll call F, which I'll also call the misfit. What is going to go into your misfit function?
The observed arrival times.
Yeah, I'll call it sometimes T, which I'll say observe. And there will need to go into it a synthetic or predicted. And I'll say might as well leave room for a weighting matrix. Okay, that'll need to go here. Something that says compare two vectors. Whoever said distance, right? So you said distance, and that's S minus M, right? You know, plus the squares and so on. Here, T minus TS, that's also a distance, right? So now we're computing a distance in data space. Here, in the forward model, this involves a distance in physical space, which is not the data space. So some way of comparing T and TS, sums of squares of the differences and so on. Of course, that's a sort of a distance. All right. We'll also need a little function that computes how to change the model. And I'm running off my page here, but I don't need much. I'll call it K. And K is what I'll call the sensitivity of this problem. Remember that in a linear problem, when we have D equals G times M, the sensitivity of the data to the model parameters is G. You want to think about it as differentiating the data to the model parameters, you have the matrix G. Here we're having a D equals curly GM situation, like here. And I've done curly G here. That's the forward model. As everywhere, our phi is some sort of a misfit. I'll call it big phi. This works on the model parameters and has the geometry of the solution. This works on the data and has a weight and defines however you judge being right or wrong. Least squares, quadratic, D minus prediction through G weighted squared, something like that. And here now, we need the prediction. We need to figure out how that gradient of G works with respect to changes in the model parameters. So if you read the notes and we talked about the linearization, then we know that we need a function that will tell us if I change my model parameters, my location by so much, how much will my prediction change? So I call that the sensitivity, as you would too. And what is going to go into it? Well, of course, the station locations again, the current earthquake location, another earthquake location again, and of course the velocity again. But now you also have one more parameter, which is the arrival times at the station. And that's because what I want you to do is I want you to take this expression and differentiate it. And that is done in the notes, but also you should be able to do it. See notes, also see Lay and Wallach, that book there, they're describing that. They're just saying, well, take a derivative, okay, on how to differentiate this. So same parameters, right? You need a station location matrix. You need an event location. You need the velocity, and you need the times of arrivals as observed or as predicted, because those things change. You need one more function, and then I need to put it together here without doing it for you. So you need a function that says, what do we need?
We need like
what do we still need here?
We need an initial guess.
No, that goes into the main function. I'm still making sub functions.
We need to figure out how much to change our guess by.
Yes, indeed. So that's a solve, or that's an inversion. This is where it actually does happen, right? In all previous work, we had a G matrix. We had a way of solving, we had a way of measuring a misfit, and we did a simple inverse on those three. Here, we have a G curly operator, a way of measuring the misfit, a way of measuring the sensitivity, which we differentiate by hand, and then we need an inversion. So I'll just call it invert. And having evaluated the sensitivity, I will need to invert it. And so what goes in here will be the sensitivity and whatever predictions I've made and whatever observations I've had. And that's this K here. And well, without writing any more, I'll say K is the sensitivity. Okay, so I'll call that thing which comes out, I should really maybe call it U. Of course, it doesn't matter on the inside, for an update. Or maybe I'll call it delta N. All right, so this is abstract, right? I think now I need to write it that way you would really do it. Now you have some sort of a main function that needs to say, you begin. When you know nothing, initialize. You got to stick something in, your choice. You know nothing about this earthquake. You want to stick in zeros, random guesses, pi e log 2. You can do anything, but from a beginning, I'll call it n0, you can make a prediction for what the times are. So you decide. T0, that's, you're stuck now, right? If you've decided on an initial model, you do your forward, because then you made the prediction. And you need a misfit, because that's how bad it is. What goes into the misfit? Well, what you have, what you predicted, and any weights you want to give based on an uncertainty or something that you will give, but without doing it, you just do nothing yet. And then you're saying now you need some kind of a loop, either a for loop, you do it 100 times, or a while loop that says as long as you haven't reached 100 times, or as long as your misfit hasn't reached a certain value, or as long as your update is meaningful, or as long as you like a for or a while. Okay, inside of this loop, I have an earthquake location, I have a data prediction, I have a misfit, I don't like it. So I will call how much my change is at this point, evaluated at this point. That's the key thing, right? So you have a solution, you calculate the gradient, which you do by hand, and you stick it inside the elements of the vector. And then you evaluate that gradient at the point where you're at. And if you have that, you have a way of using that sensitivity in your inversion step, which uses the sensitivity and the data residual to give you a model update. And then you say, and here is the only line of code then in the main thing, it says that your model is your old model plus your update. Now I'm really condensing it. So super condensed, now you know that you have a new model, and now basically your new model becomes your new guess. No longer your initial guess, but it feeds back into what your current state is. And forgive me the M0 notation because I'm condensing it here. I do indeed call it M0, and then I start calling it M. But you began, you made data, you have a misfit, and as part of a for a while loop, you're going to say, at this current location for my earthquake, how will a change in model parameters map into a change in data prediction? That's K. How do you use that then to inversion? That's the one step where you use the generalized inverse again. That gives you a delta M. That gives you a new model. That new model becomes your current guess, with which you make a forward prediction, with which you have a misfit, and you still don't like it. So you calculate the change, you produce a new update, you produce a new model, and you run around. And when your misfit drops below a level, or when your delta M is below a certain threshold, or simply when you are tired, you finish. And at every step, you can build this into as much as you like. You can plot histograms of your residuals. You can plot any cyclicity or directional angle dependence of your residual. You can look at the behavior of the mean squared misfit and so on. But that's the Geiger method. Saying it here is like, it makes sense to me, but I don't think it would make sense to you yet without actually trying it. I think you have to sit down and do it. These pieces are easy. Forward model, misfit, sensitivity. You do this by hand. In my rendition, each of them is essentially a one-liner. And I think I'm a little better than you are in condensing things to one-liner using some matrix tricks and so on, but it's very little, right? An inversion is something like, G transpose G times G transpose times whatever your data are, which is this here. How about I'll note it, right? These guys are going to give you the delta D. This thing here that we talked about, that's your physical distance, which doesn't really get any mathematical significance. This here is again that data distance that we're going to measure. And this here is going to say ultimately how a dm leads to a dd. I'm writing this again here. This here is my forward. This here is what I've been calling the sensitivity. What I haven't written here, but I suppose I should write it. Maybe I'll just write it with a loop, physical loop. How do I produce a dm from an existing dd? Well, by inversion of that sensitivity, which is the gradient of G. So that is the inversion step. Is it clear that that is the statement? This says the data prediction will change in this way according to this matrix evaluated at the current solution upon a change in the model parameters that are perturbed as delta m. So the whole thing about the Geiger method is that it says you want to produce a delta m. And so if that's the linearized relationship and you want to find the perturbations delta m, you need to apply the usual tools. I call this K here to say, well, that the delta m that will solve this problem is some kind of an inversion of this delta G, or this K as I've been calling it, times to delta D. That's what's going on. Instead of solving for model parameters that give you the data, you solve for model parameters, perturbations, that give you data perturbations. And you have to write it out by hand first to realize then that you're pretending that you're doing this, or you're doing this in an iterative fashion, which means that you're asking for those perturbations that ultimately make the move to the proper data smaller and smaller. And that gives you the stopping criterion too. If your solution to delta m is not moving anywhere, you're probably done. At that point, your data prediction, your data change is going to be so small that you're not moving your solution anyway. And at that point, your confrontation of the data that you have produced and the data that you have collected is also going to give you a misfit that is smaller and smaller. So you can must keep track of your misfit by measure the discrepancy between those, measure your sensitivity, and then do an inversion. So my solution involves writing down forward, misfit, sensitivity, and inverse separately, making them as simple as possible, and then writing a main body of the function that says do a starting solution, produce the forward data, produce the misfit, and enter a loop that says, okay, now I'm current. I calculate my current sensitivity. I calculate my current inverse based on my current misfit. I calculate my new model. That gives me a new forward model. That gives me a new misfit. And then I re-enter the loop until I drop below a critical threshold in either delta M, delta D, or phi. And remember, those things are different, right? So delta M is how much you need to move the earthquake from its current position. Delta D is how much you will change the data thusly produced if you move the earthquake by that much. Then you have a new solution, then you have a misfit with the forward model or with the data you have collected. And so these three things independently can lead you to believe that you're done with your inversion. Can't improve it, wouldn't change the data, or have sufficiently fit the data. Those are the three aspects of it. So I think this should be a little bit confusing for all of you still, because I'm actually normally I try to explain it as best I can. Here, I'm trying to explain it without doing it for you, which means this is not the best I can explain it, because the best I can explain is to really write it out and do it. So it needs to be a little confusing still, but you got to go try it. And what you're writing in your report, well, you're writing your report, well, how do you pick an initial guess? How good is it when you pick an initial guess? I mean, are you going to pick something that is in the middle, at the edge? Are you going to look at any angular distributions? Or you do whatever you want. Then You're going to evaluate the basis of judgment. You're misfit, but not just misfit. The misfit here is what drives the algorithm. But for you to decide you're done, you could also look at the distribution of the residuals or any angular dependence of the residuals and anything that you could bring to bear on your quality evaluation. You run this algorithm, you track the improvement. So show me how delta M moves around. Show me how phi diminishes. Show me how, well, that'd be most of it. Show us how the residuals evolve, and you do that. Then decide when to stop. Motivate why you decide how to stop. Take a look at the final result. Convince yourself the final result is better than the beginning. Convince yourself that the final result is good at all, but you have much freedom in it. And the key step is to figure this derivative business out once, and to walk yourself through that algorithm the way it was more fully written out in those notes I sent you, with the MK and the MK+1 and how you really think about it. All right, does that begin to make sense? It's not the full answer, and you will need to scratch your head. But then again, that's what you're paying me for, to make you scratch your head. All right, what we have now is somewhat overdue. We need to start with the analysis of time series that explicitly acknowledges periodicity. Okay, so let's put that under the big header of time series / Fourier, name of the French gentleman, / spectral analysis. So where are we with that? I think I should just maybe get out of the way a few things here. First of all, that whatever we do, I'm going to mix and match it. When I say time series, I also sometimes mean space. We're in GEO after all, so we work in physical space. And yes, we work in time, so space or time. So whenever I say frequency, which now gets a new notion, it'll be temporal or spatial frequency. I won't necessarily care that much, and neither should you. Okay, maybe I'll begin with the oldest formula in the book. Okay, let me see how to best approach it here. Throwing out some words here, I mean periodicity. Okay, so give me an example of a periodic function.
Sine and cosine.
Sine and cosine, all right? And so I also give you exponentials using imaginary numbers, using 2 pi, and using phi, which is my phase angle at this point. And I want you to know that that is an elementary function, cosine 2 pi plus I of 2 pi phi. That's Euler's magic formula. Okay. So how about this? Let's talk about a sine, which you all know, right? What do I think about phi? Really, I think about phi as follows. I think about an argument, t, let's say it's time, and I really think about that as a proportional fraction as expressed as wherever I am in time with respect to some other interval. So here, I'm going to call little t the argument of my function, and big T, that means it's a variable, right? And big T is my fixed period. And I want you to visualize the sign and think that, yep, at 0, that means t0, whatever the period is, it's 0. And then when you've reached the length t, you're at 2 pi, which means you come back around. This also means that I now define period as t, and I now define the frequency, which remember early on we were like just counting in histograms and stuff, but from now on, my frequency, in this case, which is temporal, I'll call it little f, and that is 1 over t. So you'll see me write also sines of 2 pi ft, and you'll also see sine of omega t, where omega is the angular frequency. Okay, that's just words. All right, well, so the argumentative function is the thing that varies, right? So here is little t, it's little t, it's little t, and it's as a fraction of big T or multiplied by little f or multiplied by little omega. And so f times t, and you know you work out the dimension, right? A sign of something, that something on the inside has to be unitless. You can't take a sign. It's inherently a fractional thing. So there's no units inside. So the frequency is in units of 1/seconds if it's time. So that's hertz. If it's space, it's in 1/meters. That doesn't get its own unit. Angular frequency is in radians per second. That doesn't get its own unit. In spatial oscillations, how about I do that? That's going to be useful. I'll say this is time. If it's space, and again, you'll hear me confuse those all the time. It's not important now. It just leads to different notations and different textbooks really. So I'll think about as a basic building block is a sine of 2 pi times some argument x divided by some length scale, which I'll call lambda. So here is my really changing argument. That's my variable x. And this thing is again my fixed, not period, but fixed wavelength. And my spatial frequency, I'll still call it f, and I'll call this 1/, now a length scale, okay? If this is time, this is in per second, also known as hertz. This is space, this is in per meter, and it doesn't get a cool name. Speaking of which, Siemens is not taken as a unit, is it? Maybe I can make some progress in my career there. All right, and the equivalent to angular frequency is, I'm going to call it the spatial wave number. And I'll call it K. And so K is going to be 2 pi f. Okay, so we will be writing equivalent expressions for sines and cosines. And we're also always going to do something like this, 2 pi fx or kx. And then you can go through the usual trigonometry to convince yourself that yes, if you add big T to the argument time, that you are not changing anything. Even if you add that n times, that's the nature of periodicity. You add a unit of lambda to your x, and you're just doing fractions of 2 pi. And sorry, then you're adding little n 2 pi's. And that gives you the repeated periodic segment. Should I draw at least one little picture? You want to think about the variable t. You want to think about a sine going like this, let's say. You want to think about the intrinsic length that this sets up, which is big T. And if I drew space, I'd be drawing x, and I'd be calling this lambda. And if you sit there with a stopwatch, and per second 1/t stuff comes by, or 1/lambda stuff comes by, and so that's the difference between frequency and period. And then I always want to have you think about the circle, where you will have angles, 0, pi, pi/2, 3/2 pi, and you want to think about moving through the circle with your argument t, like this, right? Or rather, with your argument phi, I'll say now, the phi angle. If I draw a phi angle, a 0, I mean this here, pi/2 and so on. And so you want to think about little t over big T, as saying, well, how many, that's the phi, which means how many fractions of this circle have I completed? And if you have big T, a long period, then you're going slowly through this circle. If you have a short period, you're going fast, and inversely the frequency. So I really always best remember like little t over something as in a fraction of a interval, really. So that here we'll be calling an interval. A duration, and same here, this is an interval of space, which is a length. Okay. This isn't necessarily all obvious, but this should all be known to you and coming back to you. All right, so what do we definitely need to talk about next? We need to talk about the notion of orthogonality. I think the quickest thing that I need to do first is I want to talk about the product of two periodic functions. And I'll be talking about over an interval, which I call a unit. And so if I take either a cosine or a sine of some argument, 2 pi, and now I'll say m times a phase angle, multiplied by a cosine or a sine of the argument 2 pi n times the phase angle, and I integrate over the phase angles, over the fractions. Remember, phi is my fraction. Sorry, that means that picture is the same, right? Phi goes from 0 to 1, but I'm multiplying by 2 pi, right? So forget the 2 pi or remember the 2 pi, 2 pi, 2 pi. So phi goes from 0 to 1 and multiplied by the number 2. The identity that I have is that I get either the number 1 if m equals the same as n, or the number 0 if that number is different. And I write this as delta m n, whereby this delta is also known as the Kronecker delta, probably the only one named after a person. Right, this is the 1 equals if m equals n and 0 if m not equal n.
There's also Dirac's delta.
Yep. You'll get that maybe next week. And thank you for reminding me, it's not the only delta named after someone. We could go on a beautiful tangent here. To come, don't forget Dirac. Well, I'm going to also give you yet one more formula, and that is the exponential variant of it. Here's I, that's our E. My imaginary number is I, so the square root of negative 1. 2 pi, I was sitting there. Here's my integer, m. Here is my phi, a fraction, as I roll around the circle, times negative I, the usual 2 pi, an integer n, and my fraction phi. And I want to integrate that against phi. No need for a 2 here between 0 and 1. And I get the same result. And I'm going to write you the intermediate thing just because I have it written here. 1 over I, 2 pi, e to the I, 2 pi. Now you get the difference between m and n times phi, normalized by, again, the difference between m minus n. I write this one because it's easier, because you've all integrated exponentials and you know how to multiply and sum their arguments. And so this is between the upper and lower limits of 0 and 1, and that is, again, delta mn. And here's that Kronecker delta, right, where you're saying 1 if m equals n, those integers, and 0 if it isn't. So that's the same formula here. Much of this stuff it needs both the exponentials and the signs. The signs are often easier to visualize, obviously a little wiggle. The exponentials are often easier mathematically, and so I feel like you should, I should have at least this. Okay, so what is orthogonality? This means orthogonality. Now remember that we had a data space and we had a parameter space. Well, now we're talking about function spaces. Sines and cosines are orthogonal to one another in the sense that when they're integrated on a unit interval, that it either becomes 0 or 1. When properly normalized, and when it's really literally 0 or 1, we talk about orthonormality. Okay, so now you have the notion of a basis. And if you take the set of functions for all indices, m, part of the natural numbers here, that the function square root of 2 cosine 2 pi m phi for any m, and the function square root of 2 sine of 2 pi of any m of an argument phi, and the function 1, that set is a basis for all real valued functions of phi that are real valued, as I've said, and have finite energy. So we're not dealing with functions that are infinity or have jumps to the size of infinity or have, weird behavior. So when we talk about real valued finite functions, finite energy functions, we mean the normal stuff. What does that mean then? Okay, this means really the following. Just charge ahead here. If I have a function, here's some function s, right? Some signal. Clearly that's going to be our time series, or temperature, or mass, whatever our physical variable is, of the variable phi, some argument. And the notion of basis in this sense tells me the following, that if I compare s with a weighted multiplication of all the functions in that basis set, to begin with the first function, and I'll weight it by the value a0, and then I form a weighted combination of this set. And so I'll say there'll be, how about I make them red? There'll be some weight a sub m, which is going to multiply the square root of cosine 2 pi m phi. And there will be a weight b sub m, multiplying my basis function sine 2 pi m phi. And I'm not forgetting the square root of 2. So it goes in here. But now I'm saying, well, look, I took 3 functions out of this set. But really what I'm going to do is I'm going to vary m. And I now sum over the indices that are the positive integers. That's the word I was looking for, z, integers. Positive integers, right? Numbers, 1, 2, 3, 4. From 1 to some upper value, m. And I'll say to m minus 1, big M minus 1. So I have exactly big M parameters because I start counting at 1. If I wanted to wrap the previous one in there, well, if m equals 0, I don't have the sine function multiplier because it's 0. And I have cosine of 0, which is 1. And so that's where the m0 term goes. So what is this here? So this is a weighted combination of the functions out of the set, of the elements of the function set. And I consider that an approximation to the function s of f, an approximation of how many terms? Well, m terms, an m-term approximation. Okay. When I say it's an approximation, I need a way to compare it, and I'll compare it the usual way. I'll subtract it. Now I have a value for every phi. This is the pointwise comparison, if I do this here. But that's not how I want to compare it. I want to compare it in the least squares norm. That's where I've been going all along. And so just like forming a dot product of elements and doing sort of a phi, which would be, a bold S dot S, which is a sum of squared values. but here I have functions of a continuous variable. I'm going to compare the absolute value squared, and I'm going to integrate it. So I want you to recognize that as our very usual least squares norm, but now in a sort of a continuous set. So now this whole thing is a mean squared comparison with all the connotations of a norm comparison and L2 and so on, because you will recognize, and I don't necessarily have to go pull out my page, maybe I do briefly when we said talk about norms and distances, and you want to recognize that that is the same thing. What is my page? Is here, right? When it was the moment for norms, the L2 norm, this was a sum of elements to the P, so P is 2 here. Forget the square root, I mean, it's in there. And then the sum, but now for a continuous variable, I have an integral, and my integration is over phi. All right, I'm running out of space, so I'm going to do this. I'm writing against my hand, and I'm about to finish here. How about this? Angled. So this mean squared comparison of this approximation is asking how much in the mean squared sense on that interval my approximation is wrong. And the notion of having a basis in this space, in this mean squared sense, means that if I up the number of terms and I let m go to infinity, which means very, very, very many, that in that limit, I can reduce the mean squared approximation error to 0. Okay, so this is a very strong statement, right? But of course, it's slightly weakened by the fact that the strongness is like this is always possible for functions out of this class. All they need to do is not blow up when you integrate them. And I don't tell you what the rate improvement is of the approximation. I just tell you that if you keep summing, you'll end there at 0. Not pointwise, you may have errors at points or at intervals, but overall, you're going to reduce this error as much as you can down to 0 in the limit. And so I'm going to write one more equation and then finish here. So in that sense, in this sense of, there is a basis and it's an approximation and there's a mean squared behavior underlying it, we will be writing often that functions on an interval of a continuous variable phi are given by a coefficient set, A of m and B of m, that will be infinite. So now I make this thing infinite. And again, in the sense, and if you wish an extra bracket here for clarity, you can have it, in the sense that they will multiply cosine and sine terms of 2 pi of that fractional 0 to 1 variable phi multiplied by these integers m here. That is the new meaning of is equal to is in the mean squared sense. This is not true at every point phi. In fact, it may be very wrong, but in the mean squared sense, it may be very right. And I need you to see that that is completely fitting with everything we've been doing. We've never tried to fit individual data points. We've only tried to fit them in the mean squared sense. Fitting, inversion, now call it a new word. It's now called an approximation. And why? Because we're now going to see how we can reconstruct a signal by finding these coefficients. We're going to see what we can learn about these things by looking at the values of the coefficients. We'll have these coefficients be random variables, and we'll talk about bias and variance and so on. And all of that is going to be, again, in the mean squared sense. And the word Fourier, so this here is a Fourier series, a representation of a square integrable signal. And I'll write the stipulation there, as long as S, when integrated over phi itself in the mean squared sense, is not blowing up by going to infinity. Okay, so we have a new meaning of is when I say this signal is that? I mean, over the interval in the mean squared sense, there is a Fourier series representation for anything that you care to analyze, as long as the signal is, not pathologically having infinite energy. So I need to finish here. And what we're going to do with that is that we're going to talk about how to find these coefficients, what to do with them, how to interpret them, and how to go from an interval which was arbitrarily restrictive, 0 to 1, even though it was the periodic cycle. We're going to deal with infinite intervals. We're going to deal with discrete and continuous sample signals and so on. But that's the basis of everything what we're going to do in the next few lectures.
Frederick.
Yeah.
Can I ask a question about the Fourier series here? I guess I'm always confused, although I've learned this many times, that why do we have to explicitly write A0?
Well, you don't. And I'm actually on my next page, most likely I'm no longer going to do it because I'm going to switch between the exponential notation and the non-exponential notation. Here, I do it because I don't want to deal with the square root of 2. That's this. This is ugly. This is beautiful. Like, people talk about beauty in mathematics. Every mathematician will tell you that this one is more pretty than that one because, ugly too.
Okay.
All right. There is not much more to it that if I wanted to wrap this inside the sum, and people do that, they would write the multiplier as square root of 2 minus delta 0m. This is a subtlety that you may not have seen, but that often arises. You want to stick that in here. I'm not going to sully my page here, but I'll be on the record, right? You fold that A0 inside, and then it becomes multiplied by square root of 2 times 1 minus Kronecker delta 0m, just to make sure that you don't need it. So am I answering your question? So this term, I explicitize it here. In electrical engineering, they'll call it the direct current term, the zero offset term, the zero term. This, we're going to go find out very soon that that's the mean of the signal over the integral. That's the mean. That's the infinite period. All synonyms here that are kind of come out here. And so, well, I don't know what the original question was other than that sometimes you see it, sometimes you don't, but always you need it because 1 is an element of the function set corresponding to a function that is constant over the interval. Everything else is wiggles around it, and maybe I should draw that here. So here's my phi, and the 1 is a function in the set, and square root of 2 is 1.4. So here's the cosine, and here's the sine. And then we're saying that same behavior happens on intervals of length t. But I'm not telling you what t is, but I'm wrapping it inside that. I'm saying, going through the whole argument of little t divided by big T as a fraction, and then how many times you are able to be inside. And so that's our way of saying this t can take many values, and you can either say phi is 0 to 1, and then you fit more t's in it, shorter frequencies. In this case, t is 1. So here's another function. The phase angle, or rather the fractional angle, goes back between 0 and 1. And now still have my constant, and I'll have, and now I draw that t is a half. And so this Fourier series says that if you think about the t, but it's hidden in here, as m increases, your t decreases. And so keep counting wiggles, an integer number times, fractions of the 1 over period, 1 over 3, the period, 1 over 4, the period. And in this sense, an enumeration of all these things will give you a complete basis for that interval of a function phi between 0 and 1. Everything does get easier with exponentials, but then you lose a little bit of that physical intuition. And since anyone in the physical sciences, and in fact I do it typically with our freshmen, is to say, well, look, the temperature of the Earth, and the Earth is rotating, so you're clearly going to get a 24-hour cycle, and sine and cosine immediately arise in that, physical space. And so the abstraction here is that On the face of it, there was nothing special to a sine and cosine. And in fact, Fourier never apparently did it, even though I didn't read his books. He used other functions, orthogonal functions too. Or maybe initially he did. So it's not the only representation of a signal. This is the Fourier representation, and we find it handy. Why? Because cycles are everywhere in nature, including, the Earth is rotating. It's tilted. You know, there's longitude and latitudes. It's a sphere. That's why we have goniometry, trigonometry, and geometry. We invented all of that mathematics because we live on Earth. We wouldn't have done it if Earth was flat. Well, it could have been flat and round as a pancake, I suppose. Does that make sense?
Yeah, it is.
Never forget the zero term. The other thing is that very, very, very often, and I have done that too, is I've said, let's just not bother with the mean shift of the signal. The mean is the easiest thing to estimate. We always take it out. We're always talking about perturbations, and I mean, how many times have you heard me say already, consider a zero mean signal, right? And then that A0 is not in there. You usually begin by taking out the offset.
Yeah, because for the seismic records, I guess the first pre-processing we would do is remove linear trend, remove mean and stuff.
Yeah, but now here, so there's an interesting thing, right? In this representation, there is no room for a linear trend. I mean, in this Fourier series, I've said only constants and cycles. If you're allowing for a linear trend, great. That's an extra component. Then you would do it because if there is a linear trend, it is not well captured by sines and cosines. And in fact, linear trend removal is vital in order to get this Fourier series to be well behaved. That's another important thing that will come out. But in climate time series, like literally I do it with the freshmen, right? We take our temperature records and we're saying, look, there's a 24-hour cycle, there's a yearly cycle. If there's a global warming trend, it's on top of that, and we explicitly include that. And what's another representation but the Fourier series for a thing on a interval? Well, take polynomials. That's a representation that'll converge at some rate. So you can just say it'll be, on an interval x plus, x squared plus x cubed. And then you have all of these, like multiple, you can think of multiple ways of representing a signal on an interval via basis functions. This is an easy one. It's a common one. It's a cyclical one. It's a convenient one. And it's rooted in the Earth because of its roundness and our rotation.